In this part of the lecture, I'd like to talk about the hydrologic structure of the surface regime. And I want to start out by talking about watershed as land area that is drained by the surface hydrologic network. We can see in the diagram on the right that we have a network of streams that start with upland streams that come together to create other streams, that come together to create new streams, that come together to create. And as we move down in this network, we are gaining a significant amount of flow that's moving through the channels. So we can talk about the amount of land area that is contributing water flowing through the outlet. The outlet, as identified in red, is that point where water is leaving a watershed. And if we're interested in knowing what portion of the land contributes water to this outlet, we need to look at the topography of the landscape surrounding the drainage network, and we can trace lines from high point to high point, and the lines from one high point to another high point represent the watershed divide, and the divide represents that portion of the land surface where raindrops are falling outside of the watershed and therefore not contributing to the outlet, versus raindrops that are falling inside of the divide and contributing to flow through the outlet. So the notion of watershed divide, separating that portion of land that is draining into a particular hydrologic network from that portion of the land that is not draining into that network, and then the notion of the outlet are key concepts in terms of understanding the hydrologic structure of the landscape. In the diagram on the right, we can see the dashed line coming up through like this, going up to the divide, the topographic divide, coming down this ridge, coming back down through here. So all of the land area inside of the dashed line, the dotted line here, represents the watershed of this particular reservoir. In other words, all of that precipitation will find its way into the reservoir. Rainfall that's falling on the other side of the dotted line will not find its way into the watershed. So the watershed of the reservoir then is that land area that contributes overland flow into the outlet. In this case, the outlet is the reservoir itself. Then we can talk about the watershed of the overall stream channel, and we can differentiate between the watershed of the reservoir and that of the outlet to Howe Sound. This is Howe Sound. This is the outlet to Howe Sound. We can talk about the watershed of this particular outlet, consisting of everything inside of the dashed line. And everything inside of the dashed line then is going to be contributing surface runoff that will eventually wind up in Howe Sound. So we can differentiate watersheds within watersheds. We call one of them a subwatershed of the larger watershed. In Minnesota, we have somewhat of a unique condition because we have continental watersheds that flow in three separate directions within the state of Minnesota. We're at the nexus of the Hudson Bay watershed, which is water that's flowing to the north and eventually into Hudson's Bay in Canada. We have the St. Lawrence watershed, which is water that's flowing to the east through the Great Lakes and out through the St. Lawrence River to the Gulf of St. Lawrence. And then we have the Mississippi River watershed, which is sending water down into the Mississippi River and eventually draining through the Mississippi River and discharging into the Gulf of Mexico. So very few other states in the country are characterized as having three continental watersheds contained within their borders. And it can be said in general that everything in Minnesota is moving downhill. However, it's downhill is the direction of downhill depends upon which of these three continental watersheds you mean. Because in the northeastern part of the state, downhill means to the east. In the northwestern part of the state, downhill means to the north. And to the rest of the state, downhill means, generally speaking, to the south and into the Mississippi River Valley. Hydrologic structure of the surface regime is the watershed area that is drained by a surface network. We can talk about the relationship of three watershed zones to land use suitability. We have this outlet, this hydrologic network of streams flowing through the landscape. They have a land area of watershed that contributes precipitation inside of this line that I'm tracing now. So this is the watershed of the hydrologic network. And within that watershed, we can talk very broadly about three different zones. The so-called upland zone, which is where most of the precipitation actually lands. That precipitation will join the runoff stream in the surface regime, or it will infiltrate and become part of soil moisture regime, or it will join groundwater and become part of the groundwater regime, and eventually discharge by surface means, by subsurface means, or by groundwater into the channel. So it's collected in the upper portion here, and then it is conveyed out of the watershed through what's called the conveyance zone. So these three different watershed zones have implications for suitability for different kinds of land uses. Generally speaking, we want to protect the collection and conveyance zones because this is where water from throughout the watershed is discharged out of the watershed. So keeping the conveyance and the collection zone unfettered by development is a means of allowing the natural functioning of the watershed in the landscape to do what it naturally wants to do, and that is discharge water from the upland areas of the watershed into the outlet. Similarly, we also want to manage the drainage buffers. We can see in the diagram on the left, we have some headwater streams here that are moving up into the upland area. What we want to try to do then is to manage the buffer regions of the collection zone and the buffer region of the stream zones moving into the upland zone. And then we want to protect the collection and conveyance zones. And once we've done the protection of the collection and conveyance zones and manage the drainage buffers, then we can talk about development or other kinds of upland uses occurring within the upland zones that are left behind. So it's very important in terms of thinking about suitability of land use within a watershed to understand where you are within the watershed in terms of water moving across, through, and underneath of the land surface to discharge at the point of outlet. So we can see this final plan that was developed, conceptual plan, with where all of the development then is occurring outside of the collection zone and conveyance zone, outside of the buffer area, and in upland areas that are contributing water to the outlet. We can talk about hydrologic structure of surface regime through a concept called stream water, the stream water drainage network within a watershed. This is systematic organization of stream channel segments or hydrologic reaches within a watershed. So we can talk about the channels that flow in the watershed, whether they be the main channel, the heavy blue line that you see that I'm pointing to here, versus these lighter lines, which are upland streams that feed the collection and conveyance channels. Two first-order channels join to make a second order channel. So we're moving from the very high upland portions of the watershed down into a zone where two intermittent first order streams are going to join together to create a second order stream. Two second order streams come together to create a third order stream. Two third order streams come together to create a fourth order stream. The systematic organization of the stream channel segments allows us to understand the volume of water that's going to be flowing in different parts of the stream network. The first, second, and third order streams are what we call headwater streams. So essentially all of these stream channels that you see here are headwater streams. Their function is to bring water out of the upland areas, drain water out of the upland areas, pass it on to the collection zone and conveyance zone. So the first, second, and third order streams here are capturing the water coming out of the upland region. The first, second, and third order streams here are capturing water coming out of the upland region and distributing it to the collection and conveyance function of the fourth order channel. So we do have a very systematic way of thinking about stream channel segments and hydrologic reaches within the watershed that allows us to understand the relative amount of water that's flowing in different hydrologic segments within a watershed. Fourth order and higher streams are collection and transport streams. They collect and transport runoff from upland areas out of the watershed. These pictures give you a sense of what these different stream orders look like. Generally speaking, the first order streams and pretty much the second order streams are what we call intermittent or ephemeral. They are flowing only when there is enough precipitation or enough direct surface runoff or enough drainage from soil moisture to promote flow. So we can see in this channel on the upper right, there is a pool of standing water there, but the water is not moving because there's not enough precipitation that's occurred within the most recent time period. There's not enough surface runoff. There's not enough discharge from soil moisture to support perennial movement of water through that first order stream channel. Similarly here, we can see a fairly well-developed channel, and all that means is that occasionally, fairly infrequently, this channel is asked to carry a large enough amount of water that will scour out this channel. But you can see here that the channel is completely dry. So this is what we would refer to as a first order channel. Pretty high up in the watershed. These first order channels are pretty high up in the watershed relative to the second order channels, especially relative to the fourth order channels. Here we can see a dry stream bed that is not carrying any water at all. Again, this is another example of a first order channel. Second order channels are in between the always intermittent nature of a first order channel and the more permanent flow of higher order stream channels. Sometimes a second order stream will in fact dry up. Generally speaking, they have a little bit of flow moving through them. A third order channel is draining a larger watershed. By that I mean that this third order channel is draining all of this land, whereas this first order channel is draining only this land. The second order channel is draining this land. And that first order drains into the second order. The two second orders drain into the third order. The two third orders drain into the fourth order. So as we increase hydrologic order, we're going to see an increase in the amount of flow that's going to occur. Here we see a third order stream channel and a fourth order stream channel. These stream channels from third order on up are, generally speaking, going to be permanent stream channels flowing all of the time. There's a relationship between stream water and stream velocity and particle transport. The lower order stream channels, the first and second channels, have a high rate of flow when they are flowing. Problem is, or the situation is, they don't flow all that often. They are not they are not perennially flowing streams. However, when they do flow, they tend to have a fairly rapid rate of precipitation because they are capturing surface runoff from the immediate precipitation, and it's draining through these first order channels very rapidly. Because they're carrying water at a high flow rate, they are able to move fairly large particles. Whereas when we get into second to fourth order stream channels, they have a moderate flow rate, less than that of a first order. And because they have a moderate flow rate, the size of a particle that they're able to transport is going to be smaller. And then finally, when we get into the 5th to 10th order streams, we're going to see a low flow rate, that is the rate at which the water is actually flowing, as opposed to the amount of water that's actually flowing. But the rate at which the water is flowing is lowest in these higher order stream channels than it is in these lower order stream channels. And consequently, they're not able to carry the same particle size that the lower order stream channels can carry. We can see with increasing stormwater, we have a decreasing number of channels within the basin. So this is the Mississippi River Basin. The Mississippi River Basin has over 1.5 million first order stream segments in it. It has over 350,000 second order stream segments. It has only one 10th order stream segment. So as stream water increases, we move from first to second to third. The number of channels within the basin is going to decrease. We go from 1.5 million first order channels to 8 ninth order channels. We're going to get decreasing total length of channels within the basin. This is the total length of streams by order within the Mississippi River Basin, and the 10th order channel, which is the very main stem of the Mississippi River, has a length of 1,800 miles, but the combined length of all 1.5 million first order stream channels is much greater than is the actual length of the single 10th order channel. The drainage area also increases proportionally, whereas a first order stream might only drain one acre, the 10th order channel drains over 1.2 million acres of land. So we see decreasing number of channels within the basin. We see decreasing total length of channels within the basin. We see decreasing rate of flow, but we see increasing area of drainage and increasing discharge of river flow. So water is moving slower, but more water is moving. And we can see then that the Mississippi River, as it discharges into the Gulf of Mexico, is a 10th order stream channel. That is exceeded only by the Amazon River, which is a 12th order stream channel. Within a hydrologic structure, we can talk about a nested hierarchical structure of watersheds relative to drainage network. So as we move from lower order stream channels to higher order stream channels, the amount of land area that's drained by the stream channels decreases significantly. In the landscape that you all are working on in this class, we can talk about the hydrologic structure of that landscape. And this map shows the hydrologic orders that exist within the study area. The white represent first order channels, the green represent second order channels, the light blue represent third order channels, the dark blue represents the fourth order channel. And then the Minnesota River, as it flows along the southeastern corner of the watershed, is actually an eighth order channel. So we have first order channels coming together to create second order channels intersecting a channel to become a third and a fourth order channel. Within that landscape, we have two distinct hydrologic structural regions. In the upper portion, you can see that there are lots and lots and lots of first order and second order stream channels, but no third order channels and no fourth order channels. Whereas when you look at the southern portion of the study area, we have a lot of first order channels, we have several second order channels, we have 3 different third order channels, and we have a fourth order channel that's collecting water not only out of that portion of the landscape, but the landscape that is to the northwest of that area. So, and that's because these two landscapes are of different ages. The northern portion was glaciated about 12,000 years ago, so it's relatively speaking a lot younger. It's been out from underneath of the massive ice sheet for a significantly less amount of time than the part of the study area in the southern part, which was glaciated about 20,000 years ago. So this landscape is 8,000 years older than the landscape in the north. It's had 8,000 more years to develop a hydrologic network, a surface hydrologic network. And we can see in detail then the first order channels that really don't go anything at all. This is often referred to as deranged drainage, mainly because the channels really don't go anywhere. They don't provide that much drainage in the landscape. Whereas in the southern part of the watershed, we go all the way down. Within the watershed, we go all the way down to a fourth order channel that dumps into the eighth order channel. This is a much older landscape, and so it has a much better developed hydrologic network.